Hello everybody. So I want to show you a very simple example of how we could use the transformation equations that I showed you in another video and how you would go about deriving these equations. So what you see here are transformation equations. So remember, if you have a stress element, our initial stress element is something like this, right? Which is kind of what I have in this example. Of course, my directions are different for the sigma y, and this is your xy axis, right? So what happens if you look at a different plane? So in this case, actually, we want to find sigma x prime and tau x prime and sigma y prime at 45-degree angle. Now, theta equal 45, when you have positive, means a plane that is counterclockwise to your x or y plane. So in other words, 45 degrees like that, counterclockwise. If we had negative, then you have to go clockwise. So positive theta means counterclockwise. Okay, so now question is, what are our stresses now on here? This is sigma x prime, sigma y prime, and tau x prime, y prime, right? As you saw in the other video. So that's our goal here. And I just want to show you that this is just a plug-in really. And what about the 45-degree angle? I just picked an arbitrary angle here. Actually, it's not an arbitrary angle. 45 is picked, so we don't even need to use our calculator. Because you see in this equation, if you put 45, 2 times 45 is 90. So cosine of 90 degrees is 0, and sine of 90 degrees is 1. So things very easy to calculate. So how do we go about finding these stresses, these transformed stresses, sigma x prime, sigma y prime, and tau x prime, y prime? Okay, first from your initial stress element here, say, okay, what is my sigma x? So remember we said if normal stresses are positive, in their intention rather, they are positive, and that's the case here. But look at the sigma y. That's in compression. So we get minus 10 megapascal. Okay, so that would be this guy. And then tau x prime, y prime. Remember, this is a positive tau x prime, y prime. So basically, if you look at the right-hand side, and that shear stress is pointing up, that's a positive shear stress, so 40 megapascal. Okay, then just plug in to the equation. So sigma x prime equal sigma x 50 plus sigma y minus 10 divided by 2 plus, so I'm looking at this equation, sigma x is 50 minus sigma y, right? But cosine 90, because when you put 2 times 45, you get cosine 90. And tau xy, which is 40 positive, sine 90. So this is 0, so that's gone. We get a, let's see, we get a 20 here, and we get a 40 here. So we get a sigma x prime equal to 60. And similarly, our tau x prime, y prime is minus, so remember, this is very important, guys. Don't forget there's a minus out here. All right, minus sigma x minus sigma y. So sigma x is 50 minus sigma y divided by 2 sine 90. And we can forget about the next term because it's 40 cosine 90. 40 cosine 90 is 0. And this becomes, be careful, this becomes positive 30 with the negative outside, becomes a negative 30. Sine 90 is 1. So tau x prime, y prime is, just erase this, use red. Tau x prime, y prime becomes, what did I say? Negative 30. All right. So now the question is, what is sigma y prime? Remember, there was a formula in the video that I showed you before this called stress transformation 1. we don't need to use the formula. Remember, we said that there is an important equation that says sigma x, if you have sigma x and sigma y, and if you calculate sigma x prime, the sum of these normal stresses on two orthogonal or two perpendicular planes must be equal to one another. So if sigma x, for example, is 50 and our sigma y is -10, so the sum has to be 40. So look, if our sigma x prime is 60, what should be sigma y prime? -20, because we want to get it to be 40. So that's how we get our sigma y prime to be -20. So here we go. We got all the things that we wanted to find. So now let me just redo this for you guys. So if our initial element was like that, oops, I messed it up. Okay. If that was our initial stress element, now at 45 degrees, right? This is the 45, right? What do we have? We have a sigma x prime of 60. That's this guy. Sigma y prime of -20, so that means compressive. Let me actually get rid of this. And what about tau x prime y prime? Let me use a different color. I have a -30. Remember, negative here means like that, pointing like that. So remember, once you figure out the direction on one side, you can figure out the direction on the other side. So that's the 30, which actually here in terms of sign convention would be -30. So you see, this was a simple example, guys. So you saw how we can use the equations that we developed in the previous video and apply it to this example. So the next step is, now I'm going to make a video talking about how could we find the maximum of these normal stresses, the maximum of this guy, and eventually the maximum of tau x prime y prime. And you already see we had a 50 here on this plane, but when we went to a different plane, we got 60. So that was an improvement. Even our 10 they became 20. But then our shear stresses got smaller, actually. It became 30. So the question is, at what angle do I get the maximum sigmas? And that angle is an important angle. And once we have that angle, we can actually figure out what are those maximum sigmas. And those maximum sigmas, both sigma x and sigma y, sigma x prime, sigma y prime, are called principal stresses. They're denoted by sigma 1 and sigma 2. One is usually maximum, one is minimum. And they're called principal stresses. So that would be the next topic that we're going to talk about. Thank you for watching and listening.